Dr. Achilles Cortellis. Dr. Cortellis has worked on numerous safety projects for the US DOT, for National Center for Transit Research, FDOT, FHWA, and NHTSA, evaluating technologies for transit buses, large trucks, passenger vehicles, motorcycles, pedestrians, and bicycles. He has worked on the technology development and system integration for naturalistic studies and conducted controlled driving experiments. In the last few years, his research has focused on connected vehicle technology safety evaluation, as well as several safety-related technology systems reviews for pedestrians and traffic signals. He has served as principal and co-principal investigator on more than 30 projects and currently works at Qatar as the assistant director of the ITS Traffic Operations and Safety Program and is a member of the Automated Connected Mobility Evaluation Program. And with that, I will hand it over to our presenter today, Dr. Cortellis. Take it away.
Thank you, Chrissy. Good afternoon, everyone. Today, I'm going to present the work we did on a project called Smartphone-Based Connected Bicycle Prototype Development for a safer multimodal transportation system. This project was funded by the National Center for Transit Research, and I would like to also present my co-team here. Dr. Pensulin was a co-PI, Dr. Yusun, who is a professor at computer science at USF, and Niha Karkar was a research assistant that helped on the project. Today, we will talk about the background and motivation of how we started this project and where we wanted to go. Different technologies we reviewed and eventually decided to use. I'm going to show the methodology of selection and how we went about designing the system, and show how the prototype of the system worked, which was the main focus of the project was to actually develop a prototype, working prototype. We obviously did some testing to be able to verify that it works a certain way, and at the end offer some discussion and future work discussion on how we can obviously improve it. So I hope I hope everyone that joined in knows this, but obviously I'll make it clear. The background and how we started this was that clearly we've seen in the last few years an increase in bicycle use and other modes, but bicycle use for as a sustainable transportation mode. So we do have especially the younger generation wanting to use bicycles to travel. Um, and However, the bicycle fatalities in the US have been increasing. The latest data we have from the FARS, the fatality analysis reporting system, is that in 2018 we had 857 bicycle fatalities, and this number has been increasing year over year. So clearly, even though we do have obviously bicycles, and that's a great thing being used, we do need to address the safety issues. Out of the 2018 crashes, the fatal crashes, 93% were single vehicle crash, meaning a single vehicle and a bicycle. 29% were at intersections, and 59% of those were at non-intersection locations, meaning along the roadway. Um, Along the roadway, and the vehicle was passing by. So this is important because it was kind of how we started figuring out what the system should be doing and the locations that we were interested in pursuing as test scenarios. Um, so as mentioned earlier, I have been working on connected vehicle technologies for the last few years. In fact, I'm working on the connected vehicle pilot from USDOT that is going on in Tampa right now in our city. And one of the things that basically is the issue here is that we have two kind of technologies that are still not connected, or I should say, let me use a different word, they're not um, integrated yet. One is the autonomous vehicles, where, as we all know, recently vehicles, not recently, but the last at least 5, 6 years, vehicles more and more come out with sensors and technology packages that detect um, other vehicles and pedestrians and issue warnings to their driver or take action and either slow down, stop, swerve, and things of that nature to avoid a crash. However, as you can see on the slide here, the bicycles remain a very difficult detection problem for autonomous vehicles because they are fairly, at least in the mindset of the computer algorithm, fairly unpredictable in the sense they are small enough, but they move fast enough that they're not considered pedestrians, obviously, and they are also on the road, meaning at least a pedestrian is expected to be on a sidewalk and then just cross the road at a specific point. However, bicycles are mixed in with the traffic, especially on low-speed roads. So therefore, the autonomous vehicle is supposed to be able to detect and figure out, what the bicycle is going to do, or how the car is going to react and what maneuvers you should take. So as far as autonomous vehicle technology, we still have this issue of basically not able to respond very well to bicycles yet. Um, and Like I said before, autonomous vehicles are required, obviously, in order to function safely. They have to be able to detect pedestrian bicycles first, and then react predictably, so that both the vehicle and the bicycle are aware of each other's location and they avoid having a crash. So connected vehicles, which is the other technology that is ongoing right now, is the idea, and I'm not talking about vehicles that come out that basically have internet connectivity. That is not what connected vehicles in this setting is. Connected vehicles is basically vehicles that um, they use a certain communication protocol, and as the picture shows there, they basically emit a specific information about themselves at a very high frequency. And therefore, if all vehicles are connected that way, they send their information, every vehicle knows where every other vehicle is, and that way you can imagine situations where you can avoid crashes. And at this time, connected vehicles are still tested. They're still in the pilot situation, and that's why USDOT decided to have 3 pilots and fund projects where the technology goes into people's cars, and then we evaluate how well it works and in a larger scale other than testing. Um, and the reason that the government has to be involved here is because this bandwidth that is used for this communication is uh, basically controlled by the FCC and protected for this use. And also, the other benefit of connected vehicles is that you can also you can connect to infrastructure. The autonomous vehicles cannot connect to infrastructure. They basically have all sensors and everything they need on board to be able to do all these calculations and figure out where things are. Connected vehicles, on the other hand, can actually talk to roadside units that are installed along the side of the road, and therefore know that I'm approaching an intersection, and the intersection is going to turn red, let's say in a few seconds, so I can let my driver know to slow down, or I'm approaching another car at a dangerous speed and I have to reduce my speed. At this time, because the systems are basically working through this thing called the onboard unit, they do not take any action on the cars. They do not have any control like the autonomous vehicles have. Therefore, at this point, they just provide warnings, so the driver still needs to react. However, in the future, we do expect to have an integration of these two technologies where a connected vehicle can, basically an autonomous vehicle can really have connectivity, and therefore, in addition to their own sensors, have this information that otherwise they cannot have, so that they can increase things like going through intersections without problems, interacting with other users better, etc., for safety applications. One other thing that is happening here with connected vehicles technology, connected vehicle technology, is that you can basically connect to any user as long as the user is able to have a certain way to communicate out. So this is where bicycles, and we saw an opportunity to provide a connection to the bicycles, because otherwise they will not be part of the system. And you can imagine also pedestrians or other micromobility users say will have this problem. So as I'm showing here, just a brief summary, the communication that is used right now for connected vehicles is the dedicated short-range communication, or DSRC. It uses a network that can connect directly between each unit, and it has pretty low latency, delay basically between the messages. There is no infrastructure that is needed, meaning two vehicles can communicate between each other without any kind of intermediary here. The volume of the data is low, therefore you can send quite a bit of information between vehicles. And however, you do need to have an onboard unit or an OBU. This is kind of like a small computer that is the one that is responsible to send and receive the messages. It also has a GPS unit and other sensors. And that's basically the primary use of how it communicates with others. The onboard unit, however, is you can imagine it's a bulky system right now. When I say bulky, think of an old-style phone or an external hard drive. Actually, I shouldn't say that. Those are pretty low. Um, um, yeah, like an office a desktop phone. That's probably what best describes it. And also the other thing that is needed is power. So obviously, to be able to use such a system, you need power, which on a regular bicycle is non-existent. There is obviously ways to provide that. You can add batteries. You can add, yeah, that's the main way. But it becomes increasingly difficult to do that. Plus, you have to have additional, systems on your bicycle to be able to do that. So there is a second technology that is actually increasingly, this came after the DSRC and is increasingly being used right now. It's called the cellular V2X, and the V2X means vehicle to everything technology. It uses standard 4G or 5G in the future cellular connectivity, and it's actually believed to be faster and more efficient than DSRC, than the previous technology I mentioned, um, especially the 5G speed that we now see coming out. It uses obviously existing infrastructure network, and because the cellular providers are increasingly improving their systems and their networks, and they will provide the capability for this anyway, this technology can be used instead of DSRC, or in addition for that matter. The other good thing about this technology is that it's basically communication between smartphones, and therefore, since smartphones are widely used and everybody has them, well, when I say everybody, obviously increasingly larger number of people, at least it's a platform where they don't have to buy additional equipment or install additional equipment on their bicycles to be able to participate. Also, there is no uh, like I said, bulky OBU onboard unit that needs to be installed, and you do not need an additional power for this. So we decided to go with a second technology, obviously, and again, this is the new technology that is coming out now. Um, and to proceed with the project, we had to decide a certain kinds of parameters to use, obviously, to design this. Um, Really, we had to develop this algorithm that controls the data transfer between devices and this system that will be responsible to provide these warnings that we decided to provide. We had to develop the application and test it, collect data, analyze, to fine-tune the parameters or change certain things to make it to improve the capability, and then test again and verify the application. So the way we decided to go about this was that it would be a little bit different than the other systems. The main difference, as you can see in the picture there, is that every user, and I'm including obviously pedestrians here because it can obviously everybody can potentially use it. That's also one of the benefits of using a system like this. But every user, instead of communicating between each other, they actually communicate with a cloud server. So again, the data transfer that I mentioned happens between each user's phone, say, and a server which is dedicated for this application. It's online, therefore it's using the existing 4G, 4G or 5G connectivity. And clearly, when we go to 5G, we expect the speeds to increase to the point where they overpass the other system, the DSRC system. Um, and the reason for this is that the data transfer between each user and the cloud happens fairly fast. And the other big thing is that the server now is responsible to make all the calculations necessary to decide which user is in danger and which is not in danger, so that they send the appropriate alerts to the user. The DSRC technology uses the onboard unit, which is basically a small computer, to be able to do all these calculations, and it's just receiving the data from the other users. In our case, the smartphone is basically the data generator, primarily from the GPS unit, and it's also used as the HMI, is the human machine interface, which is really what it means is the display or the way you provide the warning to the user. Um, so therefore, the idea here is that it's an application where all users can use to provide their location and other variables, and then receive the warning once is determined in the system that you are in danger or a potential collision course with another user. Another benefit of this is that basically using this online server, we do have a very powerful processing platform compared to the limitations that an OBU or a small computer might have on the unit on each car. Um, Another one that I actually just thought about adding is also the fact that a smartphone, depending on, it does not matter how old your smartphone is. As we know, the older a smartphone gets, it does have limited capability. Things start not working, applications not working. But this is fairly agnostic on this because the data we will collect is very basic, and therefore people with older smartphones say can participate. It doesn't require you to have the latest and best smartphone, and this is crucial if we're talking about a system where we expect, you expect it to be ready and a lot of people use it. Then this has to be the case because clearly not everybody has the latest and best smartphones. The the design of the system, as far as how we decided to make it work, is that since we want it to be compatible with the DSRC, which is an existing technology, we basically follow the DSRC protocol. The DSRC protocol is what the connected vehicles use right now. It's a Society of Automotive Engineers J2735 protocol standard, where the main communication method between vehicles is the basic safety message, or BSM. The basic safety message has two parts, and the first part, which is the core, data element is basically the variable, excuse me, the variables you see on your screen. So uh, I have the name there and the description. The first one is a message count. So each message that goes out has a specific number, has an ID that is temporary and changes for security and privacy reasons. We have timestamp in seconds. We have latitude, longitude that is taken from the GPS unit. We have elevation. So all these three come from the GPS unit. There is an accuracy variable that tells you how accurate the position is. And as far as the vehicles go, it also includes a transmission state, meaning what gear you are in, if you will. It has the speed of the vehicle, the heading of the vehicle, therefore you know direction, the steering wheel angle, the acceleration in three axes, and the brake system status of the vehicle, meaning if you're braking or not. Now, in our case, first of all, since we're using smartphones, we need to make sure that which of these variables were able to be provided by the smartphone. And as you can see, everything was able to be provided except the three variables there that are related to the vehicle. So the transmission, the steering wheel angle, and the brake system status were not, you cannot provide those from a smartphone. Plus, we don't really need those in the sense a bicycle doesn't really have the need to provide that information. So given this, we obviously wanted to include all these variables in the message that the bicycle would be sending out, and therefore uh, it can be as compatible as it can be with existing system, existing vehicles out there. One other difference is that as far as the one of the parameters we selected to use is the basically the decision of okay, when should I inform the users that are alert the users, warn the users that are basically within a dangerous situation. In most of the autonomous and connected vehicle applications that are doing this job right now, one of the main factors used is the time to collision. This is TTC. Time to collision is basically the time it will take in the near future to end up in a collision, and it's calculated using the speed of the vehicle and acceleration and obviously the position, how far you are from the other user. We decided not to use this variable because the differential speed between the two users, being one is say a vehicle and the other one is a bicycle, the differential speed is usually fairly high, meaning a vehicle can obviously travel, fast speeds, and a bicycle there is a pretty there's a cap up to what speed you can travel usually. So, because the difference can be high, we decided to use the stop inside distance, which is a traffic engineering terminology where it's the distance calculated and needed for you to be able to safely stop your vehicle, say, if you see that there is an obstacle in front of you and you have to stop your car. And it's used in engineering of the roads, and that's where the speed limit comes from. And it's the safest way to calculate something so that, okay, if I provide this distance, then the vehicle can safely stop without ending in a crash. So you can think of it as the maximum distance needed here. That's the formula, and I'm not going to go into detail of it. It just uses its two portions. The first one is the perception reaction time. It's the time it takes, the perception reaction distance, which is basically based on the time it takes for the vehicle driver to react, see and react to the obstacle they have to stop for. And the second one is the distance traveled while you're braking your vehicle. Now you can see here that we have basically speed included here. We have the time, the driver reaction time, gravitational constant, the deceleration rate, which is the deceleration basically of the vehicle, and it does include the grade of the road because in inclines and declines is different. Now, for our application, we basically said that we're going to use flat roads for now. However, there is a way to actually include, based on, again, your GPS data, if you're on an incline or decline, and adjust that. So using this formula, we can include things like the acceleration of the or the deceleration of the vehicle and the bicycle and the speed, and figure out, calculate this distance. For our system, we basically equated this distance to a radius or a distance, if you will, around each user. And as you can see here, I have the three users that we used. And again, I include pedestrians because this is, it can very well work for pedestrians as well. So each user has their own radius, if you will, around a circle or a buffer around them. So imagine this as a safe bubble of a minimum distance that if the two, so, and I'm referring to, say, the vehicle and the bicycle, if, say, you have a bicycle moving and then a vehicle comes behind them, as soon as the two bubbles touch, meaning, the distance between them, comes to R of the vehicle plus R of the bicycle, then the warning will be issued because they came to a certain proximity that we need to alert them. So what the system does, using the data, the instantaneous data that it gets from the GPS of each user, it calculates this distance all the time. However, we did put minimum distances, meaning it doesn't matter what your calculated distance is. If you reach this minimum value, definitely send an alert. So for vehicle, it was 20 meters or 65.6 feet. For a bicycle, it was 10 meters or 32.8 and feet, and for a pedestrian was 5 meters. And obviously, these can be adjusted. In fact, we did have to adjust them and fine tune them as we did testing. So as I proceed here, this shows it's kind of like the logic of the algorithm that is making all these decisions, and I'm going to explain one at a time the sections. And as you can see, we have on the left, we have the side where things happen on the smartphone, the mobile application. And on the right side, I have what is happening on the cloud server at the same time. And to focus, so the sections I'm going to describe are basically the authentication process, the data collection, the calculations, and finally the alert that is set out. So the first section is the authentication. So the application is basically any other application that you can have on your phone. You install it, and it has an authentication method where you authenticate yourself as a user via an email. You have to check your email. You get a verification link. You verify that you're that user, and what it does, it basically assigns everybody a certain ID that is just a garbled mix of letters and numbers that obviously it can become fairly secure, so nobody can track anybody. And you can, we did it through email, but you can, of course, the authentication method can be via text, via other ways. But the idea here is that this is the process where each user sets up their account, if you will, and therefore they can participate in the system. And I'm going to show a little bit later the method or what else you can do once you do that. The second section is where after you become obviously a user of the system, and now you can start using the system. And the way you do it is basically the idea is that once you decide, okay, I'm going to take a trip, I'm going to be in my car or I'm going to be on a bicycle, and therefore I want to use this application, you can start the application, and the application, what it does at that time, it's sending to the server the variables that we talked about, the location, as far as latitude, longitude, the elevation, speed, acceleration, and those kinds of things, right? That are collected from the smartphone. So this is monitored at the server level from the users, all the users, and the idea is that it calculates, not the idea, what it calculates is that distance that I mentioned earlier, the safe distance, if you will, the bubble around you. And if it notices, so up to this point, this is the data collection. our system at this point was collecting data at the frequency of 1 hertz, which means once per second. And this limitation comes from the GPS global position system chip inside the phones at this time. And after that, the server is basically doing the calculations where it calculates this radius of the circle of the buffer that I showed before. And the system checks if two or more users or circles intersect, or if they're going to come to proximity to intersect, or if they have reached their minimum values that I mentioned before. If either of the two happen, then the system will reach to the final point where it will alert the two users via notification or an alert on the phone that you are basically in close proximity to being a crash. And that is where we can provide different warnings for different applications. Sorry, different scenarios, depending on how the users are moving at the time. And what I'm showing here is basically a screenshot of the say the phone while the application is working. The first one on the left is the when you're trying to connect in, and as you can see, you can put your email password or create an account to begin with. If you have already created the account, you can sign in. But at this time, you can also select what type of user you're going to be. So you select bike, car, or pedestrian. And the idea here is that if you select this, the system assigns this minimum value that I mentioned before to you as a user. Therefore, it knows that you're basically as a bicycle, or you're a pedestrian, or you are a car. These can be changed, of course, to any kind of mode you want, but in this case, that's the three that we added. And the second screenshot there you can see is really the authentication after you sign in. Um, and I left the email user and the user underneath just to see that's kind of the idea that the system sees as, okay, I'm this user right now, I'm entering the system and I'm going to be a bicycle. And you can see at the bottom there we have the sign out when you're done. The verify email is to verify your email when you make your account. And then we have a start activity and stop activity. That's where you would press once you are ready to start your trip. So if you do that, you start your activity, and then on the third screenshot, that's basically what the application is showing while you're running your bicycle. So the idea is that you can either put it in your pocket, or you can have it in your, wherever you can have it. If people use it as a GPS navigation system at the same time, you can put it on your handlebars and go about your way. The application works in the background as well, and or you can hear music or whatever it is you want to do. And then the last one shows an example of a notification or a warning where it was determined from the system that you come to proximity with another user, and therefore, as you can see, it says warning collision threat. That's what we tested. It was the basic one. However, in the future, we'll work on customizing the warnings depending on the movements of the users. So to to test this application, we came up with three scenarios that came from the idea from these scenarios was from where the crashes happen, and it was three different scenarios. The first one uh, is the common interactions between a bicycle and vehicles on the streets. The first one is called the opposite direction, and as you can see, yes, wrongly we show that a bicycle is going the wrong way uh, on the side there. Actually, the bicycle is going the right way, but the vehicle is going the wrong way. It doesn't matter. The whole point is that the two are going opposite from each other. The second one is the same direction, where the most common situation where a bicyclist is on the bike lane or on the sidewalk for that matter, and a vehicle is coming from behind, passing by next to them. Now, in this case, clearly this is obviously not necessarily a problem. However, we do see quite a few crashes, and this is known from work we've done with crash analysis in other projects where we find that sideswipe or a vehicle passing with not enough distance passing distance from the bicycle, that's where crashes happen as well. Um, and at the worst case, sorry, at the best case scenario, these can also um, be as a reminder of both that, hey, there is a, I mean, if I'm a vehicle passing by, I can just get a reminder, there is a bicycle here, pay attention more than usual. The last one is an intersection scenario where uh, the two come at about 90 degrees. I mean, the angle can vary actually, and we have allowed a different range of angles because clearly not all intersections are at 90 degrees. And this can work, you can imagine, at any kind of intersection. It doesn't have to be signalized. It can be a stop sign. And the other thing I should mention is that even though I placed these on the road so that you can kind of see and visualize it, but if for a moment you kind of just imagine that there is no road behind, it's just a blank space, this application clearly works in space and time, right? So it doesn't matter where I am, as long as there is somebody coming from behind me, or if I'm a bicycle, or from in front of me, or from the side, this application will work, right? So it could work if I'm in the middle of the field and or the desert, and somebody else is coming from the side. So, but since we are driving and using roads, that's where we are placing the scenarios to be able to test them. So I'm going to show results of testing we did, and this is clearly just one of them. Clearly, we've done several runs, if you will, of each scenario. But I'm just going to show one example so that you can see what we get. So the first one is the opposite direction scenario where the vehicle and the bicycle are going different directions. This is an actual test we did at the USF campus. Um, so that the vehicle is going, as you can see, towards the west. The bicycle is coming towards, sorry, the other way around. Vehicle is going towards east, northeast. The bike is coming southwest, and the basically the yellow dots there represent the bicycle while it's traveling at the normal condition, as we call it, meaning nothing is happening, and the blue is the normal condition for the car. So what happens is that as the car is coming uh, towards the right here, when it reaches this point here, this is where the first and the red here, the red three dots, is where the car received the warning. So basically, we changed the condition from normal to the warning. I'm getting the alert here, and this vehicle got three alerts. And the reason we did that is because we said, okay, should we just provide one alert and that's it? And for the testing of this application, we said, no, we are going to continue providing the alerts as long as the conditions are met, meaning as long as the two users are within the proximity that we want or less than that, we will send alerts to both of them. And then when the situation changes and they just leave each other, then we're going to stop doing that. So the vehicle is here when it got the first alert. The bicycle is here when it got the first alert. And as you can see, the bicycle only got two of them because the bicycle was only going at 7 miles per hour. The vehicle was traveling at 30 miles per hour. And basically, by the time the bicycle got the second alert, the vehicle already got three alerts and passed it, right? So once the vehicle reached this point here, it was already passed clear the bicycle, and therefore there was no reason, the distance increased, and there is no reason to be alerting anyone. Um, so again, this is an example of the opposite direction test, and we've done several of these, and we collected information so that we can fine tune the distances and all that. Um, and what I'm showing here is the situation where it's the data and where we got the alert. So what we have here is three different pieces of information. The first one, the blue line, is the distance. So as you can see, the distance starts the y-axis is on the left here. So it starts at 80 feet. I'm sorry, 80 meters. And it obviously keeps going down, meaning the two users are actually coming close to each other, right? The second piece of information is the time to collision, and I calculated that just so that you can see how it would work with a time to collision, which is a standard, uh, uh, piece of information that is used now. And uh, usually the threshold for that is about 4 seconds. If your time to collision is 4 seconds, that's when traditional applications provide a warning. Um, and the the green line, this green line here, is where there is actually an alert or not. So as we can see, it's obviously zero. There is no alert. And then I just have it's a stepwise thing where it shows you, okay, for the first second, it was second number 5, 6, 7, and 8. We got an alert, right? And then it went down to zero again. So what I'm showing here is the from the previous this test here, and you are seeing the 3 seconds, basically what it is, the 3 seconds that the vehicle got the warning, as long as it was close enough to the bicycle. The the next one is the same direction test, where similarly, we did a test where the bicycle and the vehicle are traveling in the same direction, and again, and you can see the arrows here. They're going both. The vehicle is traveling at this direction. The bicycle is traveling at this direction, and the first warning for the vehicle was right here. As you can see, the blue was the normal conditions. The red is when it received the first warning, and the bicycle received the first warning here. So clearly, the bicycle was, the vehicle has still not reached the bicycle at that time. As you can imagine, remember the circles around them. But that's the whole point, is to alert them before it happens, especially the vehicle. Um, the vehicle is passing by and it received 3 warnings. The bicycle received 3 warnings, and then after that, the vehicle passed the bicycle. Therefore, we stopped the warnings. So again, the vehicle was traveling at 25 miles per hour. The bicycle was traveling at 80 miles per hour in this test. And the idea is that they should be receiving, if you remember those circles around them, since 20 meters was the minimum for the vehicle and 10 is the minimum for a bicycle, it should be 30 meters. What about 100 feet? This here shows the data for the moment of warning here. So again, the three pieces of information. If you look at the distance, it's coming down from 50 meters down to about 30 here. As you can see, when the warning happened, when the green line is going up, and for the 3 seconds that they received the warning, and obviously the distance keeps going down, and then it starts going up enough that it will stop. And then also provide the TTC, as you can see, the time to collision, so that you can see that variable as well, how it varies. Um, and the third one was the intersection scenario, where, as you can see, we have an intersection here. It's actually what it is it's a side street coming out in the main street, and the bicycle was actually traveling on the bike lane there. Um, what you see is that, okay, the vehicle is traveling here and it starts receiving the warnings at this point. The bicycle is receiving the warning first here before it even crosses the road. And the reason we have red all the way here because, and the last ones are blue because clearly the vehicle did stop at this position after the bicycle passed. And keep in mind also, because this calculation and all these things have to do with your speed and your acceleration, right? If your speed is zero because you stopped, then clearly there is no need to provide any kind of warning to anybody because you're stopped. So you're not a factor anymore. That's why that's blue at the end. In this test, the vehicle was traveling about 20 miles per hour, but you can imagine that it was decreasing to stop at the intersection here, and the bicycle speed was 7 miles per hour at the time. So what happened is that the vehicle was going by to make a stop at the stop sign here. It's a stop sign here, and the bicycle is traveling at a fairly constant speed. It did not stop on the bike lane. Um, and here I'm providing this data so you can see it's a little bit smoother situation. However, we do get the warning for a lot more because while the car is coming to a stop there, it spends a lot more time in proximity to the bicycle. Clearly, in this situation, it wouldn't be necessarily a problem because the car is stopping anyway. But the whole reason about this scenario is that we do have situations where either the bicycle or the vehicle do not stop, right? So that's kind of the idea, that they would warn them to be more careful in this situation. Um, and yeah, similar to others, that's kind of that's the data we collected at the moment of warning. And what I'm showing here is the vehicle side. The bicycle side is similar to this, it's just different scales. Um, so for future, basically at the end of the project, we had a proof of concept prototype that was successful. We were able to do what we set out to do. One benefit is that this system can work for all kinds of users. So you can be a vehicle, you can be a bicycle, you can be a pedestrian and use the system and still receive, the warnings that we want. Some of the challenges we have, and we were working towards solving them, is that the the frequency of the location points at this point is 1 per second, and it's limited because of the GPS chip, like I mentioned. But this can be improved by extrapolation algorithms, where you basically fill in the gaps, if you will, between the seconds, and you analyze the trajectory of the users. And it is expected to improve in the near future, and there's actually a few methods to do that now, but we didn't play with that yet. The accuracy of the smartphone's GPS is low at this time, and it needs to be higher for, to make it 100% for safety applications. So therefore, we will have some false positives and negatives at this time. However, like I said, we do expect that the accuracy of the smartphone to increase, and there is actually methods to do that now. There is some phones in the market that do provide higher resolution of the GPS measurements. Um, Another one is that, as you all know, if you use the GPS, basically if you use any navigation application right now, it drains the battery, right? So one of the things, obviously, if you're in a car, is not necessarily a problem because you can plug it in and charge it at the same time. However, if you're on a bicycle, that might be a problem. There is actually work that a colleague here has done at Qatar, where they looked into the application having a kind of it's a smart application where, based on your speed as a user. So if you have your phone sitting on your desk, it doesn't do anything. But once you start moving, at a certain speed, it kind of detects by itself, and it can wake up the application and start the GPS at that time by itself. So there are ways to increase the battery, performance, so that you don't drain your phone. Um, the next steps are actually to fine-tune the algorithm, and instead of those circles that I showed, to you use an ellipsis shape. In other words, so someone can say, well, it's not as important to look left and right of the user. Maybe it's more important to look front and back, and using an ellipsis shape instead of a circle might be better. So that's kind of what we are looking to implement in the future. And also we kind of did this here, we tested it, but you can add a direction verification, meaning you can verify that the user is coming from behind you, or from in front of you, and or from the side, because we have this thing called heading, as I mentioned earlier, from the GPS. So we know, the angle at which they're coming at you, let's say. And therefore you can customize the messages and say, okay, if somebody's coming from my left, I can say, look to your left, there is, or that's where the danger is, say, or from behind or from the front, and you can kind of customize messages that way. Like I said, this was tested but not implemented in this scenario, or in this first phase of the project. And that is all I had today. I think we can open it for questions. I'm sure we have some time for it.
All right, thank you very much. Okay, everyone, you'll see a question and answer pod on your screen. If you have questions about today's presentation, just go ahead and type those into the box and we will read those aloud. We do have a few questions that have come in already. So what is the benefit of using a central system versus a decentralized system for data exchange?
So as I mentioned in the past, one of the problems that you have when you have a decentralized system, meaning each system or phone or OBU has to do the calculations and all that, is that you need a pretty powerful unit to be able to do that. So if we're talking about implementing this for a majority of people, and we decide that we're going to use a smartphone, I mean, remember the title was smartphone based system, we decided to use the decentralized system so that, sorry, the central system so that we have a more powerful application for calculations and therefore be able basically not be restricted in that manner for the performance.
All right, great. Next question here is, so the usefulness of this application would depend on having a high adoption rate, is that correct?
Yes, absolutely. Just like any of the connected vehicle systems, you're right that basically the idea is that everybody or a majority of people will have an application or have a way to connect to the overall system. Yes.
Okay. Have you considered scenarios such as urban canyons where GPS is unreliable?
Yes. So as part of the other project that I mentioned, the connected vehicle pilot, one of the pilots is actually New York City. So you can imagine they have serious problems with GPS accuracy there. And there is a way to increase the accuracy of the GPS, meaning you don't increase the accuracy necessarily, but you increase the confidence that you're getting a good information. But I did not go into this here because of time. But yes, there are methods that you can increase the accuracy. Now, like I mentioned, overall, the GPS of the phone is not necessarily accurate enough now at this time um, um, to be able to do this. But in the near future, because like I said, we've seen more and more increase in phones that and technologies that do have higher accuracy, it will be implemented. And clearly, we do research on things that will happen in the future.
Okay, great. Next one here is how do you deal with the fact that there could be hundreds or thousands or even more users in a network that the system has to deal with? How do you know who is close and who is far?
So that's a good question. Basically, there are methods, and we started implementing this. So imagine a system where everybody would be connected. How do you deal with that volume? So the there are computing methods for scalability, and therefore the idea here is that we will be able to change, have geofences, say, where we know we have kind of like a grid, and all the users within a certain grid would be monitored, together, because clearly I don't need to know about somebody that's 100 miles away or for that matter at the next intersection. So therefore you can set up a grid network where you can only deal or you have to only deal with the people that are around you up to a certain distance, obviously, and you kind of compartmentalize that way the calculations.
So the decision to go with this technology seems arbitrary. In a world with DSRC connected vehicles, how will the connected bicycles participate?
Um, so, so actually there is research, and I should say that in the past year, the cellular V2X technology that I mentioned, there has been development of systems and roadside units where NOBUs, where basically can handle both at the same time. So it's kind of like a bridge between a DSRC system and a cellular system. So therefore, the idea here is that in the near future, when I say near future, I'm even talking this year, we will see applications where a system can handle both technologies without any problem and change messages between them. So we don't consider this to be a problem at this time. Again, we're designing for the future. So, and there is actually interest from car manufacturers and a couple of them, at least that I know of. Ford, for example, is experimenting with the technology, at this point, and I think Hyundai as well is experimenting with a technology that is this cellular to vehicle 2X technology.
All right, looks like we've got time for one more question. To deploy this to the general public, is there any type of regulatory hurdle? In other words, is CV2X available today?
Yes, so like I mentioned, the CV2X is available. The only I guess issue would be the determination of the bandwidth to be used. Now the DSRC has a whole control system for the FCC controls the bandwidth there, but the cellular to V2X communication does not. and it doesn't need to because it's using the regular cellular communications. The only issue there is to be able to abide by the same rules that the DSRC abides, meaning, the ID that I mentioned that changes, there are certain protocols for privacy and security that you need to follow. But other than that, all those are actually standards that they can be employed in the system right now. So it's not anything that needs, years and years of development.
All right, great. Well, we're about out of time. I want to thank everyone for joining today's Cutter webcast. If we didn't get to your question, then just we'll follow up with you via email. If you have any additional questions, please reach out to us. We hope you'll join us for our next Cutter webcast on February 27th with Shiwan Jiang talking about the Healthy Buddy program. Please take a moment to fill out the survey that popped up on your screen. Have a great rest of your day, and we hope to see you next time.